In the last 7 days alone, 4 of the tightest physical constraints holding back human progress completely shattered. For the past decade, we've been living on promises. We were told the future would be faster, smarter, and cleaner. But underneath the hype, engineers in almost every major discipline have been quietly slamming into hard physical limits. Artificial intelligence is expanding so fast that it's physically running out of electricity here on Earth. Meanwhile, the mass adoption of electric vehicles has stalled because the lithium-ion batteries powering them are simply too heavy and take far too long to charge. In the digital realm, quantum computers remain too error-prone to be useful for complex problem-solving. And in medicine, genetic cures for rare diseases still require years of broad, systemic treatments that often arrive too late for the patients who need them most. But over the course of a single week, across 4 entirely unrelated fields of science, researchers pushed past the theory and began active, real-world deployment. The roadblocks have been cleared, unblocking the next 20 years of technological growth. By the year 2030, global data center power consumption is expected to double, reaching nearly 1,000 terawatt-hours. AI is consuming electricity so rapidly that some companies are facing a reality where high-end chips sit idle in warehouses because the local power grid cannot support them. To bypass the limitations of the terrestrial grid, tech companies like Google and SpaceX are looking up. They are actively developing programs to launch data centers into orbit, moving the compute directly to the energy source. In orbit, solar energy is constant. Without an atmosphere to filter the light or a night cycle to interrupt it, orbital satellites can harvest 24/7 solar power. While the cost of launching hardware remains high, the trade-off is a dedicated, unconstrained energy supply that never needs a fuel delivery. This diagram illustrates the new engineering hurdle. Generating 100 megawatts for an AI data center in space requires solar arrays and liquid cooling radiators up to 1,000 times larger than those on the International Space Station. Because space is a vacuum, heat from the chips doesn't easily dissipate, it builds up rapidly. By decoupling AI from the terrestrial grid, we trade local power shortages for orbital engineering challenges. While latency and thermal management remain active constraints, moving data centers to space removes the immediate energy floor that has threatened to stall AI scaling. Down on the ground, the transportation sector has been fighting its own physical constraints. Mass electric vehicle adoption has been slowed by the heavy weight and limited energy capacity of traditional lithium-ion batteries. Major automakers like Dongfeng, Chery, and Factorial Energy have officially pulled solid-state batteries out of the laboratory. They are now testing prototypes in real vehicles under extreme weather conditions. This chart shows the raw leap in energy density. While standard lithium-ion peaks well below 300 watt-hours per kilogram, these new solid-state prototypes are consistently hitting between 400 and 600 watt-hours per kilogram, effectively packing double the energy into the exact same physical space. For a driver, that translates to a vehicle capable of traveling up to 900 miles on a single charge. And when you do finally need to plug in, these batteries can accept massive amounts of power, charging from 10 to 70. With commercial production targeted for 2027, the raw economics of global transportation are about to shift. The most stubborn logical barriers to owning an electric vehicle have essentially been erased. In the digital space, experts have long known that quantum computers could theoretically crack the encryption that secures the global internet. But because quantum qubits are incredibly sensitive to noise and prone to errors, everyone assumed a functional attack was decades away. This week, researchers from Caltech and Google proved that assumption wrong. They successfully demonstrated a highly efficient, low-overhead implementation of Shor's algorithm that bypasses those massive error correction limits. This graph highlights the danger. The hardware requirement to break standard 256-bit encryption collapsed from an estimated several million physical qubits down to just 25,000. Out of an abundance of caution, the Google team chose to publish their findings using a cryptographic zero-knowledge proof. This means they were able to mathematically verify that the vulnerability exists without actually handing a blueprint over to attackers. By drastically lowering the computational threshold, this algorithmic optimization accelerates internet security timelines by decades. It forces an immediate, mandatory upgrade to quantum-resistant cryptography for any institution protecting long-term secrets. In human biology, the limits have been equally stubborn. Historically, curing rare genetic diseases has required years of extensive research and broad systemic drug treatments that often act too slowly to save patients with aggressive conditions. But a clinical milestone just changed that timeline. Doctors successfully treated an infant suffering from a fatal metabolic disorder using a highly personalized CRISPR gene editing therapy. Researchers used lipid nanoparticles to deliver a CRISPR payload directly into the patient's liver, correcting the genetic mutation in vivo. This approach targets the specific underlying cause rather than managing secondary symptoms. KJ Muldoon is now thriving and preparing to go home. This single milestone demonstrates a new pathway for medicine, a future where precision gene editing cures for ultra-rare disorders can be developed and deployed in months rather than years. Energy, transportation, computation, biology. Because these four distinct bottlenecks broke at the exact same time, the infrastructure of the 2030s and 2040s will operate under an entirely different set of physical rules. Our daily terrestrial systems will be managed by highly capable autonomous AI agents that draw their processing power from data centers orbiting hundreds of miles above our heads. Down on the ground, we will commute in ultra-efficient solid-state vehicles that rarely need to be plugged in. And when our bodies fail, we will rely on rapid, hyper-personalized genetic editing as a standard pillar of healthcare. For years, science has been stuck in a holding pattern, testing theoretical models in closed laboratories. Now, across every critical technological sector, humanity is actively executing real-world deployments. As the Artemis 2 mission breaks free of Earth's orbit and sets a course for the Moon, it serves as ultimate proof of our momentum. The constraints have been lifted, and our next great leap is already underway.